Hey, how are you doing?
Hey, I think it actually joined with my work Zoom account. I don't know. I think I
Okay.
shouldn't be in trouble for doing that, but whatever.
Okay.
Hey, how's everything?
It's okay. Hanging
Okay.
in there. I have like this, so and like that.
Uh,
So, all right, let's do it. What do you want to work on?
Thank you so much. I know you're like trying to solve so many things right
Yeah, I
now.
know. It's okay. Yeah, yeah. It's cool.
Okay.
Let's do it.
So I actually wanted to work on some questions related to osmotic pressure.
Sure.
The question actually was question 15 on the biopack.
Yeah, can you share your screen?
Yeah. My computer is extremely slow today. I don't
Yeah.
know. Okay. Can you see it?
Yeah.
Okay.
Okay. So this is gonna be basically something that just makes more ions.
Mm-hmm.
So here, I mean, I can write the formula down for you as well, but you don't really need it. But osmotic pressure, it's basically this pi.
Oh
Um,
yeah.
yeah, okay. So that little lowercase I is just the, wait, I don't know what happened. Is just the, oh, okay. So yeah, the lowercase I is just the amount of ions that are made.
Mm-hmm.
So yeah, scroll, let me see the choices. Okay. So, so yeah, so we're the lowercase I is just, it's like,
Yeah, because so they gave that formula and I really wanted to understand like osmotic pressure because I feel
mhm,
I was like, okay, so osmotic pressure is a colligative property, which is
mhm,
like basically depends on whatever you're adding as a solute
mhm,
independently of the properties of that solute, right? So
mhm,
it's kind of like related to concentration, right?
mhm.
So whenever I started looking at osmotic pressure, they said that I was like, what is osmotic pressure? And then I came up with a drawing that was this one. As a matter of fact, I'll show it to you.
Mhm.
What? How can I move this? Okay, this one. Oh no, not this one.
Mhm.
Wait, let me see. I have so many things open.
Mhm.
Mm. Basically, it was just a drawing showing that water would follow. Oh, this one. That water will follow the area that was more concentrated. Can you see it?
Mhm.
Okay, the water will follow the area that was more concentrated, and that difference in pressure was what we call osmotic pressure, right?
Mhm.
And so they started talking about the difference between hydrostatic and osmotic pressure. And so that's when I got confused and I was wondering if you could help me like with that. Because then I started wondering why water actually follows wherever it's higher concentration. And then they said it was because it was trying to lower the free energy of
Yeah, in our notebook, look at content Roman numeral 2, kidney.
okay. Let me refresh it. I guess it's not gonna be working from here either. Ugh.
Wait, it isn't for me either. That's weird.
No, but I know like the entire day my computer has been, I think my computer is about to be like, you need to change me because I've had this for like 7, 8 years now.
Yeah, wait, I don't see it either. That's weird. Kidney.
Okay, so I finally opened it.
Mm-hmm.
Roman numeral, you said. Takes a while to load. Okay, so which one? Content 2?
Yeah. Hit that and then kidney, but it's not
Okay.
showing up for me, so I don't know if something happened. Oh, okay. There it is.
Yeah.
Okay, so it is working. So yeah, if you like kind of scroll down, I kind of so yeah. So basically, so I drew like so this is kind of like what happens in the glomerulus or whatever.
Mm-hmm.
So that's a blood vessel there. And something with water basically exerts pressure called hydrostatic pressure.
Why does it exert? Because of the water that's in it?
Mm-hmm. Yeah. So basically, like in at the glomerulus or whatever,
Mm-hmm.
and the Bowman's capsule, like for it to go from the bloodstream into like the Bowman's capsule, like it needs to like your blood pressure itself is like an example of hydrostatic pressure.
Okay.
So, and it's pushing against like the walls of your arteries and stuff and your
Mm-hmm.
veins. So, that water, has like its own like pressure, right? And as that pressure rises against, so it's kind of like the thing that you saw with that osmotic, that U-shaped thing with the osmosis and semi-permeable membrane in the middle.
Right.
You imagine the Bowman's capsule as that semi-permeable membrane. It like why would it? Because if it hits some type of there we go. So I mean okay, it's going to be pushing against that, right? And why would it be able to go through instead of just bouncing back? Because it exerts pressure against it. So as it exerts pressure against it, it causes filtration. So that's when hydrostatic pressure is higher. That's why I wrote like hydrostatic pressure causes
Okay, hold on.
filtration. Mm-hmm.
Let me see if I understand. So this part right here is the inside the Bowman's capsule, right?
Mm-hmm.
So this will be the semi-permeable membrane, and then there is hydrostatic pressure inside the Bowman's capsule, which is what? Urine or blood?
Yeah, I drew that like okay, so yeah, blood vessel has exerts hydrostatic pressure, which gets filtered like through the Bowman's capsule, and then it gets continuously filtered into eventually urine. That's when hydrostatic pressure is greater than the osmotic pressure. But as the osmotic pressure increases, so that's basically like as you go down from the cortex to the medulla of the kidney, the salt concentration of the surroundings increases. So that causes an osmotic pressure, which basically causes the kind of like water to go in the opposite direction.
So
So
which
that's
will
what
be water would go back to the body, right? I like
yeah.
reabsorbed.
Mm-hmm. Yeah, reabsorbed and then back to the blood basically. Think of an example. Okay, think of like making pasta. Like let's say you take like the hard pasta or whatever, you put it in water and you like boil it. So there's less water inside of the pasta than there is in the pot, right?
Right.
So there's basically water, it's going to exert hydrostatic pressure against that like a piece of pasta, and that pasta is going to have basically an osmotic like it's going to exert osmotic pressure in the opposite direction, not letting the water inside of it. But that's why we raise the heat. You can even add salt to make the osmotic pressure like higher, and so the water is going to go into the pasta, and then the pasta is going to get absorb some of it and get bigger and softer. That's just
Okay.
like
I think I understand why you said no. I
Mhm.
love your examples. This
Yeah,
is
yeah,
why
yeah.
I was like, please, I need to meet. No,
Yeah,
but I
yeah, yeah.
understand what you said, but there's one thing. So the osmotic pressure is basically the same quantity that opposes the hydrostatic pressure difference.
Mhm. Yeah.
So when they were talking about an example of reverse osmosis when they were filtrating water,
Hmm.
so they say that the only way to reverse the movement of water would be if you apply a force equal to that pressure, right?
Yeah. Think of a osmotic pressure as like a sucking kind of force. And the
And
hydrostatic,
what is hydrostatic pressure? A pushing force?
yeah. So if you go to that diagram that you were showing me of that U-shaped thing.
Actually, what I did was I opened the, oh, it's here. Never mind. Yeah, I kind of replaced it by my notebook tab because I opened it from my favorites. So
Oh, okay.
yeah,
Um, uh, let's see. So basically, like,
I
um,
can open it though. Do you want me to open it?
no, it's okay. But basically, what you have is just a semi-permeable membrane, an area where there's water and like no solute, right, and an area with water and high solute concentration or whatever.
Right?
And so, the thing with the high solute concentration doesn't have, since it has, so sorry, the part that has the high solute concentration, since it has solutes in it, it's not 100% water, so therefore it's less water, and there's more water on the side that has no solutes, so it's going to exert an osmotic like pressure against that semi-permeable membrane, and it's going to cause the sucking in of water. And you see the same examples in like one of the things you had open with like cells and stuff. Like if you put a cell in like a hypertonic environment, water is going to be sucked out of it
Mm-hmm.
because the osmotic pressure of that hypertonic environment is high, and it sucks the water out of the cell.
Right.
Mhm.
What is creating that pressure? The solutes, right?
Kind of, yeah. It's kind of like diffusion, basically, because if there's solutes there, there's less water, and
Oh,
so
yeah, which is what I show you that that's when when I saw that difference in pressure, that difference in height, I thought about um
Mhm.
oh my God. Um hold on. I'm forgetting everything today. Uh, about and not mechanical energy. I thought about
potential energy,
I'm sorry?
like gravitational potential energy.
Yeah, like potential energy, right? I thought about potential energy, so I was like, is the potential energy what's really, is it the same thing? So basically they gave the formula of density times G times H. So then that's when I remember like, okay, is that potential energy? And that's what they're saying that osmotic pressure is. Or is there any association between that and potential energy?
You said
Between osmotic pressure and potential energy?
well, I mean, if it's gravitational potential energy, then you know it's going to be pulling the water down, and so the osmotic pressure would have to be like higher than that in order for it to rise to a level that's higher. But that's just because of there's going to be more water added to it.
Okay. Um, okay, so and then the other thing that I was wondering was why is it water going to the, why is water being sucked again? Is it because I want to understand the concept
Uh-huh.
of free, like why is it leveling the free energy, or how is concentration
Mhm.
related to free energy?
Yeah, just think of it basically just since there's more solute there and therefore less solvent, all the thing, it's like how diffusion is high concentration to low concentration.
Diffusion
Osmosis, yeah.
is high to low, yeah.
Osmosis is the same thing, but it's just high concentration of water to low concentration of water, right? If there's a high solute concentration, that means the water concentration's lower.
Right, basically, and the reason why osmosis is because there's a semi-permeable membrane. Otherwise, it would just occur through diffusion, I guess. Otherwise, the solutes would just diffuse to the area of lower concentration.
It'll still, it's still diffusion. It's just called osmosis with water. But yeah, let's say the semi-permeable membrane is just, they call it semi-permeable because it means that it's not permeable to the solute, but it's permeable to the water.
Mm-hmm.
So that's just why, the only reason, it's called semi-permeable. So that means only water can move. And it just moves because, like, one side it's 100% water, other side it's not 100% water. And so water will move from where it's more to where it's less.
Okay.
Yeah.
I think I went a little bit too far.
It's okay. Just think of it as
I also wanted to understand
sucking
thermodynamics,
pressure.
so I'm sorry.
Think of it as like a sucking pressure that sucks water.
Right, and this relates also to I mean, the example you gave there, they talk about the hydrostatic and the osmotic colloidal pressure of the arteries, and how you can use that to I believe there were a couple questions. I don't even remember anymore. I did them a while ago. Whatever.
Yeah.
Okay, so based on that, I picked C only because I don't know why I picked C. I guess.
Yeah, because
the concentration and then the amount of ions will be higher.
Yeah. So comparing MgCl2 and CaCl2 will still have a lowercase I value of 3. Whereas NaCl makes 2 ions, right? So and then you would multiply it by the concentration. So the osmotic pressure for A and B will actually be this, 3.4. So okay. Yeah. So anyway, yeah, you have the right idea.
The formula here?
Yeah, it just, I wrote it in the newest one, but whatever. It just basically just the amount of ions it makes, and then the molarity of it.
Right. So then if they had the same molarity, they could be equal, but because calcium chloride has higher molarity, then I guess it's more.
Yeah, it's called the Van Hoff factor.
Van Hoff factor, yeah.
I think, the lowercase I. So basically, it's the product of molarity and the Van Hoff factor. So osmotic pressure for A would be 0.3. For B would be 0.4. For C, it'll be 0.6. And for D, it's 0.5.
For C, it will be 0.6 because it's 3 times 0.2.
Yeah. I mean, it'll be technically that times R times temperature.
Yeah, but
RT is the same for everything, right? I'm just looking at, the I and the M part.
Okay. Okay, cool.
Mm-hmm.
Okay. Wow. It took me whatever. I'm not even gonna tell you how long it took me to, because I really wanted to see I don't have a good definition of thermodynamics. So not psych. Hold on. We already did all of this ones. This is configuration. Oh, we didn't do this one, did we?
No, we could do it.
Okay.
So, okay, that's the rate. And then if you change the volume, or no, if the volume is that, what's the total number of molecules, right? So, okay, basically we have 2 micromolar per second.
Mm-hmm.
So we're going to basically convert that into molecules. So, okay, it'll be like 2e-1 whatever moles.
But
Yeah.
don't you have to, since it's over in micromoles, micromolar,
Mm-hmm.
I mean that's already two times 10 to the negative 6. Or like,
Mm-hmm.
why are you saying 2e to the negative 1?
Oh, e to negative 6.
Oh, okay, so it's 2e to the negative 6.
Yeah, 2e
Oh,
6
okay.
moles of ATP like per second, right?
Mm-hmm.
Um, and then uh, so here, so yeah, so 2e neg 6 like moles per liter, right?
Mm-hmm.
Per second, right? So
Mm-hmm.
then I multiply that by 1 e neg 3 liters because the volume is 1, milliliter.
Right, so it is 1, yeah, 1 times 10 to the negative 3, sorry, 1e negative 3
Mm-hmm.
liters. The total number, oh, this is easy. Wow. This is just
Yeah,
math.
and then you multiply it by 60 seconds because it's after 1 minute to get rid of the seconds, and then they're saying molecules, so then you multiply it by um Avogadro's number.
Ooh, okay, yeah.
So it'll be 2e neg 6 times 6e 1 times 1e neg 3 times 6e22. So that's
Are
basically,
you writing it down somewhere?
yeah, it's
Oh,
kind of
okay.
hard to,
I know. I mean, I can write it here.
yeah. But yeah, I wrote it down. So 2e neg 6 times 6 here. I'll erase that. 6e1 times 1e neg 3 times 6e. Avogadro's number is 23, right?
Yeah.
Okay. So it should be that. So let's see, 36, 72. Wait, that's not right. This is moles per liter. Okay. 6. Okay.
Wait, you divide, oh, let me see where you're writing.
Mm-hmm.
Okay. So 2e, why are you multiplying by, why are you multiplying by 1 times 10 to the negative 3 ml, liters? If, so if there's 2
Oh, to get rid of the
moles,
liters is the denominator.
I'm sorry.
So the 2e6
Uh-huh.
is moles per liter.
Right, and then we need to get how many moles are in 1 milliliter, right?
Yeah, so to get rid of the liters, which is in the denominator, I multiply it by the volume, which is 1 e neg 3 liters.
Okay, and then that, what is that, 6E1?
Yeah, so it's actually moles per liter second.
Okay, but why is the 6 there?
Oh, because it's in after 1 minute, so it's 60 seconds.
Oh, so you're already doing the whole thing. Got it. Wow. All right.
And then
I was like step 1, step 2.
Yeah,
You're doing the whole thing already.
and then moles is in the top. So we want, molecules. So 6E23 molecules per mole.
Mm-hmm.
Yeah. But then that would give you like 72 something, but I don't see any answer that's like that. So I think
We did something wrong.
yeah, because that principle, that like first number isn't like that. But then let's see. 24, 19, 13. Let me can I see those choices?
Yeah. Oh.
Wait, that's weird. It's asking, why is it saying mole? And then it's asking for molecules. So
See, it's
maybe
a constant rate. If the volume, what is the total number of ATP molecules?
if it's moles, then we don't do the Avogadro step. So then it would
They're
be,
saying molecules though.
yeah, but all the choices are in moles. So then it would make sense then. Then it would be 1.2
Times 10 to the negative
uh
7.
yeah, I think so, yeah.
Yeah. Because I get
Mhm.
12E negative 8, and then that will be
Yeah.
equal to 1.2E negative 7.
Yeah. Yeah, they effed up.
That is that the type of things that they're gonna do on the test? And then I'm gonna be there like, why is my answer not correct? And then I wouldn't realize that it says moles because I would just read molecules and multiplier and be rechecking my math.
So like
Probably.
this is what you do, since we wrote it out, and so the things I wrote out, I know that 6 times 6 is 36, 36 times 2 is 72, and since I don't see any 7.2 there, and I see the choices are just like 1.2, right, and 3.3, so I can think, what can I change here to get something like 1.2? I can get rid of that other thing with the 6 in it.
Mm-hmm. Which
So
is Avogadro's number.
yeah, because if it was asking for molecules, then you'd multiply it by Avogadro's number, which it
Mm-hmm.
is asking, but they messed up.
They're asking for
Yeah,
molecules, but okay,
yeah. But
cool.
yeah, worst case scenario, you would look at it and be like, okay, to get, a number like that.
So you do have some help with the answer choices, kind of
Mhm.
type of thing.
Yeah, always. You always do. Okay, so something that's basically like whatever, two positive, right? So you have two things. Is it magnesium or is it cobalt? Um,
I don't even I don't even know what the question is asking me about.
oh, like what could take place? What can take the place of Fe2, right? So it would have to be another ion, like a cation with two, with a two positive, right?
Right, in this case, well, Fe2, it's two positive, and then why are they mentioning the square planar binding domain of hemoglobin?
That's just, I don't know, like
That bullshit.
I mean, like in hemoglobin, like, yeah, it's true, like, the
I mean,
iron.
like, it's true, but is it necessary?
Yeah, I guess, because like, if it's because Mg2 plus and cobalt 2 plus are both, you know, dications,
Mm-hmm.
but we in order for it to be square planar, right, it has to, like, I think it'll be cobalt.
Okay, but in order for it to be square planar, or you want me to choose the answer already?
Wait. Magnesium or cobalt? See, like, because they both have two positive as its charge. I was gonna guess cobalt because, but wait a second. That's like one of those. I was gonna guess cobalt because it's a transition metal like iron is. But cobalt might be one of those special ones that has like half filled subshell or something like that.
Let me.
You could see, yeah, in the maybe like periodic table.
Yeah.
In the AMC one, it like it.
Oh, they have a periodic table. That's true.
Mhm. So like cobalt. Okay.
Yeah.
It's not one of the. Okay, so let's go with cobalt.
So you're saying that cobalt is the one that would make an exception. Where's magnesium though?
Well,
Here.
yeah,
Okay. Yeah.
it might be magnesium.
Okay.
I'm gonna
So,
guess cobalt because likely to be found in place. Damn it.
I mean, why is iron there?
What's that?
Or like what makes iron special to be the cation that's in the binding domain of hemoglobin?
Um, well, um, I don't know how to answer that question. But I was gonna say that copper is also something that so horseshoe crabs and lobsters have copper instead, and that's why their blood is blue.
Oh, I didn't know that.
Yeah. Um, so yeah, let's check out cobalt.
Okay, let's see what happens.
Okay, there we go. Yeah, it's a transition metal.
The answer to this question is C because cobalt is closely related to Fe as a transition metal and can support a square. Okay, what's up with that square planar coordination environment? I don't know what that means.
Yeah, so it just so I guess you can like look up square planar.
Mm-hmm.
It's like that's just like the shape of it. Like it's like Fe in the middle, and then yeah.
Square planar.
Yeah, just that. And then yeah, image search. Yeah, so it basically looks like that shape. So it looks like, square, right? And
Right. Yeah, I mean, this is electron configuration stuff, right? But
mhm,
what is it like?
yeah, like
I don't know if magnesium.
yeah, magnesium doesn't have. So look, in order for those different shapes to exist, you need d orbitals.
That's
And,
true.
and d orbitals are only in transition metals.
Mm-hmm.
So those, because there's empty d orbitals, which means that it can make those more complex kind of shapes.
Mm-hmm.
Yeah, coordination complex. If you just Google image search coordination complex, so if you go back to that and just type in coordination complex, yeah. So yeah, so see how these things are. So like cobalt, you see, like that's like it basically it's basically just able to make all these different. See, you see nickel also, like on the right, underneath. Yeah, right of that.
Here.
Right to the right. You're
To
going
the
left.
right. Sorry.
Yeah,
Is
right.
that okay? So this
Wait, so right
one
up.
more. This
There we
one.
go. So that's
Okay.
nickel.
All right.
So see, so these are like coordination complexes. They're basically, think of it as like it's complex, so it's not simple. Like magnesium doesn't have extra d orbitals to be able to have room to
Mm-hmm.
make all of these like coordination complexes, but like cobalt and stuff does.
Mm-hmm.
Like that cobalt thing has like, that's called like octahedral.
I think it's the same thing with is it sulfur? But for whatever reason, sulfur also has sulfur is able to make 8 instead of having 6 pairs of electrons is able to have an extra pair for an extra bond, right?
Oh, I mean, like you're talking about, well, I mean, like sulfur, like
Yeah.
it can, like in nature, it exists as S8, but it has like, it doesn't make cations or anything like that. So yeah, it can bind to 6 things because it has 6 valence electrons.
Yeah, but sulfur in some cases there was an exception with sulfur that it's able to bind actually with 8 electrons. And they say it's because supposedly yeah. So it's able to make 5 bonds instead of the typical 4.
That's 6.
Sorry, 6. I don't
Mhm.
even know where right is right, left. I don't know how to count anymore.
It's okay. So
Oh
yeah,
yeah.
sulfur can make that same shape. You're right. It is the same shape. It is an octahedral. Um, but those are actual bonds. Like sulfur is actually bound to the fluorine, right?
Mhm.
And
Yeah.
then if you hit back, now these coordination compounds, they're a little different because they basically exist as so like click where your mouse is right now, or where it was. Yeah.
Here.
Mhm. So it looks similar, right? But see how it's still 3 positive?
Mm-hmm.
That's
Yeah.
because the transition metal is still a cation, and these ammonias, they're basically like, kind of think of it as like solvating. They're making they're so imagine
Yeah.
like cobalt, and you put it in a solution of ammonia. It
And it's surrounding the cobalt. But
Yeah.
how come it shows us bonds though?
Um it's just how they like write it, because it does kind of like it is kind of like a bond kind of. It's just if you look up chelating agent,
Mm-hmm.
um that's ch, I'll write it in the chat, like ch.
Like that.
Yeah, there you go. Chelating agent. Oh, chelating ligand. Yeah, so like a chelating agent, that's basically how it's working. um yeah, like scroll through, you kind of see like um yeah, like maybe click that one that's chelation therapy or whatever. um it's, where's your mouse? Okay, go
There.
left. Yeah, there we go. So yeah, so we have EDTA here, and so see how they're, so like those dotted lines.
Mm-hmm.
So yeah, the other diagram, it looked like legit, like, whatever bonds, but they're really not. They're kind of like just, they're like salt bridges or ionic bonds.
Kind of like ionic interactions or like,
Correct. Yeah.
can we say like London dispersion forces type of thing, but with ions? I don't know.
Yeah, just ionic bonds that aren't really like, super strong, or
Mm-hmm.
like salt bridges.
Mm-hmm.
You look up like salt bridge, you should get like, kind of like a similar kind of thing.
Mm-hmm.
Or you'll probably get something that says like, like voltaic cell. But yeah, because salt bridges, that's how a lot of things work with enzymes and stuff.
Mm-hmm.
like at the active site, right? So yeah, that's kind of like an example. Electrostatic interactions.
Mm-hmm.
Yeah.
Okay. Um,
So yeah, so basically that's also there in chelating agent, also there, with that solvation thing around like that coordination, like in a coordination complex. They're
a
basically just like
chelating
that.
agent is what I've heard about chelating agents, but I don't know.
It's like a metal that you use to kind of, yeah, you could look at like, I guess, the slide over there or whatever, it'll tell you like
This one?
like underneath it.
Oh,
So like let's say you have like arsenic poisoning or something, it'll just, it'll solvate it. It'll like take the like, yeah. So like let's, because like these are like metals, right? So let's say you have whatever, so like something, right? Like too much
okay.
of like the metal,
Uh-huh.
it acts as a chelating agent. So like it'll uh yeah.
It would bind to the metal
Yeah,
or
yeah, yeah. Through making a coordination complex with it.
okay. But the agent is something
The
outside the metal though.
the metal part is the thing that works on the, sorry, the chelating agent is the
Chelating
thing
agent is the
that,
thing that works on the metal.
yeah, there you go.
Got it. Got it. Got it. Okay. All right.
So yeah, this one basically it's cobalt because it has extra d orbitals, so it can make those types of more complicated um coordination complexes like square planar.
Right. Yeah, and then magnesium is not able to do that.
Mm-hmm.
I mean, this is just it's ligase. No?
So it's going to be a kinase, right? But
ATP dependent
kinase is a type
phosphorylation.
of something. So how does a phosphorylation happen? Remember with the STY?
Right. So, oh no, it's yeah, okay. So basically, how does ATP phosphorylation or like phosphorylation happen? You're basically removing one phosphorus from ATP or
Mm-hmm.
like from any phosphorus containing
Yep.
compound, and then you're transferring over it to the other compound.
Yeah.
So the transfer is
Yep.
why did I reviewed this last week? I don't know where I had it, but
It's okay. But yeah, it's a transferase. Yep.
okay.
Because we normally think of it as a kinase, but what is a kinase, right?
Right. So they're actually a kinase is actually a type
Type
of
of transferase.
transferase,
Mhm.
right? Okay, yeah, that's what I was reviewing when I was going over the citric acid cycle, that I was like, what is the difference between both? Okay.
Yep.
Okay.
And a ligase brings like things together.
You know
Like
why I
it
thought
ties it
ligase? I
together.
thought about
Like DNA
ATP.
ligase.
Right. But I thought about the ATP pump, like the actual ATP
Uh,
synthase.
okay.
Synthase. So that is not, that is a synthase enzyme or whatever.
Okay.
So what is the difference between the ligase and the synthase or whatever? Because it's like two similar things.
Mm-hmm.
I don't know where
Yeah.
it was.
So yeah, since the synthetase causes a synthesis of something, which is bringing parts together to make a whole,
Mm-hmm.
ligase does the same thing. Like it ties it together. Like
But one of them is ATP and the other one is not. One of them
um
is ATP dependent.
Well, if they're asking about phosphorylation of something, right? You know that it's transferring a phosphate from an ATP to something,
Mm-hmm.
right? But like synthetase, since it makes ATP,
Mm-hmm.
like it'll basically combine to make it. So that's why it like synthesizes it from other parts.
Hold on,
Mhm.
I want to look up something. I had to stop sharing so I could do open Anki.
Mm-hmm.
Okay, so it's actually actually I can share here. Oh my god, the dog downstairs
Oh yeah.
always freaks out whenever he hears an ambulance.
Yeah.
Okay, so the one that
Oh,
I
there
was
you go.
yeah, so the one that I was confused with was the lyase, which is addition and removal of functional group. And then part of the lyase, there's a synthase, which do not use ATP.
Mm-hmm.
But
What in the bottom?
right. So the lyase, so that's why I got confused. So the lyase can actually use ATP to add a functional group or do not use ATP to add a functional group, right?
It seems like lyases, you will have within that group synthase, which can, I suppose, make something without the use of ATP. And then for ligases, you actually have, a condensation reaction, aka dehydration synthesis.
Mm-hmm.
So, you know, uh, it'll be using whatever ATP. But
Do you always need to use ATP in dehydration synthesis?
just for the synthetase,
Okay.
but no, dehydration synthesis basically. Wait, okay, but I mean, like, yeah, condensation reaction, aka dehydration synthesis, uh, involves the removal of like some, like it involves the creation of water, but it seems like it's a ligase. It does this using energy from hydrolysis of high energy molecules. Okay. So
Maybe I made a mistake.
hydrolysis
I
is
don't
the
believe anything you're reading there. I was the one who wrote that note.
no. So no, it makes sense. Hydrolysis is the opposite of condensation. So it's going to, I think, take a high energy molecule, let's see, find synthetases which use ATP. So I guess ATP is hydrolyzed to make something, I guess. Let me see. ATP synthetase.
Well, that's the synthetase that makes ATP in the electron transport chain.
Yeah. So okay, ADP plus inorganic phosphate, right? And then through the addition of H plus, it seems, let's see, makes ATP and water. So it's still an overall, condensation reaction. Water is given off. And hydrolyzed. Yeah, I'm not sure about the hydrolyzed part.
The hydrolysis part?
Yeah. Let's see. ATP synthase versus synthetase. Let's see. Synthetase. Um, okay. Yeah, I'm not really sure exactly, but I'm sure you're right in your notes.
Hopefully.
Yeah. But I
Okay.
mean, as long as you know like those greater, the greater
But and not
criteria.
even because like the answer choice was ligase, and I thought that I confused it with. Oh no, never mind.
Mhm.
I saw it's ligase, so that's what I thought it was ligase because it
Mhm.
uses ATP.
Uh-huh. Yeah. So basically what you're writing here, so it hydrolyzes ATP and it takes that energy to cause some type of synthesis, right?
Right. But in the actual phosphorylation based
Yeah,
on ATP,
you're not using the energy, you're just literally taking the phosphate and you're taking it from ATP and you're putting it on something.
okay.
Whereas yeah, ligase will use energy from the ATP to do something.
Okay.
Yeah. And then hydrolase is like, through the addition of water, something will break apart.
Mm-hmm.
Oxidoreductase, something that's involved in redox.
Right.
Mhm. Okay, let's see. Which of the two products was detected during the experiment? Let's see. Compound 1 makes 2A and 2B. One of them were intensely colored. Okay. So it's probably going to be the C.
My gosh, Shane, you haven't even read the passage. What is this? I don't even know what they're asking me for.
I mean, I could be wrong, but usually if things that make a lot of color, remember azo?
Yeah.
It has a lot of, you know, conjugated double bonds.
Right. Because
So
we talked about yeah, you explained that to me already.
yeah, so it might wait. Yeah, it could be that.
Okay. Let me students develop procedures to measure the kinetic parameters for blah blah blah. They utilize compound 1 as a substrate since it produced compounds 2A and 2B. One of the products was intensely colored. Which of the two products was detected during the experiment?
Yeah, you can scroll through it. Let me see if they say anything about detection.
Yeah,
Um,
like why do you assume that the
spectroscopically, like they monitored it using spectroscopy, right?
where does it say that?
Second to last paragraph. Rate of reaction 1 was monitored spectroscopically. Oh, and then X axis of figure 1 is fluorogenic substrate.
That's great.
So
Mm-hmm.
fluoresce. So it'll have to make that fluoresce, right?
Mm-hmm.
So I think it should be C. I mean, that's my guess.
Why not D?
D, mixed phenol and
Not
quinone,
relevant to the actual fluorescence type of.
I think. Yeah, conjugated double bonds.
Oh
That
my
makes
god.
sense.
Yeah.
And like, yeah, I knew because like it said on the top, one of them was very colored.
Right. Yeah, that's true. But then I
One
will
of
be
the
like,
products was
okay.
intensely colored, right?
Mm-hmm.
And yeah, so that means if you ever see that, it means it has conjugated double bonds, like
Mm-hmm.
azo.
Does it mean that it's also going to fluoresce though?
Yeah,
Because ASO doesn't fluoresce.
it does. It just that it fluoresces in regular light, so that's why it looks red. I mean,
Oh,
urine with azo, yeah.
so fluorescent is necessarily not.
I mean, like in experiments, we use, like some type of molecule that fluoresces at a specific wavelength.
Mm-hmm.
So we can like, you know, like monitor its intensity, right? But like azo, for instance, it does fluoresce, but just under regular light.
Okay.
But it's still, fluorescing. It's just it's fluorescing like a light bulb fluoresces, right? It just gives off
Right.
like a light and color.
Right. I thought that, yeah, it's fluorescent doesn't necessarily mean like, like shiny or like, that fluorescent color that you associate it to. Okay. Okay, got it. What is the value in km and what is micromolars?
Mm-hmm.
For the WT enzyme.
Mm-hmm. Okay, let's see. See how it says KM and it says see figure 1.
Mm-hmm.
So we got to look at figure 1. Okay. Now KM, right? That's like whatever the concentration at half V max, right?
Right.
V
So,
max is like 1.7 or something. So we're
mm-hmm,
gonna look at like point like 8 or something.
mm-hmm.
So like around there, it seems like it's a little bit higher than 1. So like 1 point.
Close to 2.
Let's see. Yeah, I think so. Or like, wait. Yeah, I think so.
I mean, so it's 0.8. Wait. So the half B max is going to be 0.8, which is around here.
Mm-hmm.
What about 0.6? Oh, this is 1 already. So
Mm-hmm.
1 point. Ooh, maybe 1.31 though.
Yeah, okay, let's see. So um let's see. Oh, wait. I see 1.31 in that equation. So I forgot that equation. Let's see. V naught is equal to something times at S, then that plus S. Is it like KM plus S?
Probably.
Because I see the 1.31 in that equation, right?
Yeah, but what is 1.732?
Oh, wait, you're right.
Because
Okay,
that's
okay.
also an answer choice.
All right, let's see. Let's see. Well,
I guess
we
we
could always
have to
plug
know the
stuff.
formula
We
for
could always plug in the stuff, but
who
let's
wants to do that.
all right, let's see. Let's see. Can I see table 1?
Yeah.
Um,
I mean, I guess we can do the formula. We can plug in. But I feel if we just look at the graph, it would be 0.8. Even if let's say it's 1, it's still like not, it's more leaning towards the 1 side than the 2.
yeah, let me see. So at 0.75 V max, it's at 1. 1 micromolar. Okay.
Oh, wait.
Yep.
A 0.75 is 1 micromolar.
Mm-hmm.
So yeah, it has to be 1.31 because the
You're right.
half Vmax is 0.80 something.
Yeah, I think you're right.
Yeah.
Okay. Now they said to look at the graph, but I wonder if it's like 1 over k cat something.
I should know that formula probably. But why is it that you're doubting about or are you confused about the fact that it says 1.732 and then 1.310 in the formula?
Yeah, I thought like that could like give help us out for a sec.
Mhm.
Let's see, V naught formula. What is it? Equation called Michaelis-Menten, I think. Yeah, it's V max times substrate concentration over Km plus substrate concentration. So that number,
Vmax. Oh, so that 1.73 is Vmax.
mm-hmm.
So if we knew the
It makes
formula,
sense actually, because
yeah.
yeah, that's what it is up there. Mm-hmm.
Mm. Yeah.
Yeah. So yeah, but wait, so you were able to find it out based on looking at the graph. So good job.
Thank you. I mean, I thought it was simple, and then you were like, hold on. And I was like, I really think it's 1.3, and then you were still looking at something. So maybe I was like, I'm missing something that he's saying that I'm not.
Yeah, I was trying. Yeah, I was trying to look at that equation, but yeah, the equation also would have helped us. Then I was trying to see if 1
But
over
even
that.
so, let's say we knew the equation, we didn't even have to plug in the numbers though, because it was there.
Yeah, yeah. It just that 2 choices were in the equation, and it's
Mm-hmm.
just a matter of which one is the km, right?
Right.
Oh, you know what? All right, now I know how we could have figured it out because it's V max overall, and V max is in like molar, right? Whatever concentration per second, right?
Second. Mm-hmm.
So if it has to be on the top, then
Molar per second, and then substrate concentration is in micro. Well, it's also in molar though.
yeah, overall, just yeah, think of it as molar
Everything is in molar. Well,
because
km it's not.
because K like for here, like whatever substrate concentration, it's in micromolar. V naught is in nanomolar per second. So let's just think of it as molar.
Right, yeah.
So, but since so like it's in per second, right?
Mm-hmm.
So it has to be since that's V naught is equal to this stuff in the equation, right? And it's
Right.
a question of like, is V max going to be the 1.732 number in the numerator or the 1.31 number in the denominator? Now, if it was in the denominator, then it would be like the units would be messed up because it would be like something molar per second as a denominator, which is really going to turn into seconds over molar.
Mm-hmm.
Whereas,
Yeah, because we have molars. So Bmax is molar over second or molar per second, and then times molar over molar times molar, right? So over molar plus molar.
yeah, which is just still going to be molar per second. Because
Okay.
it's like not like
Not
dividing it.
multiplied. Yeah.
Yeah. So yeah, so that's like another way we could have like you know like made sure that we were right on this because like one of them has to be V max, right?
Mm-hmm.
So and it has to be the thing in the numerator. So yeah.
Okay. Oh.
In each variant substitution that took changed the side chain. Okay, so look all the way on the bottom of the table.
Do you know these questions?
I mean, like, kind of. So all right, valine to alanine, I guess. Whatever M was, methionine to alanine, like leucine to alanine, isoleucine, I think, to alanine. So alanine is like, small. So decreased steric constraint should be it. Alanine is like the amino acid with just one methyl.
What is the WT?
Oh, that's just wild type. That's
Okay.
like how it is
So,
without a mutation.
right. So here's saying valine is being changed by alanine and at position
Yeah.
86. Okay.
Mhm.
So all of them are changed by alanine, and then alanine is a small amino acid, so that's why you say decrease steric constraints. Right? Is that what you want to go for?
Yeah, it should do that. I wonder if that affects the KM in the right way, but whatever. I that's what Alan. I mean, yeah, yeah. Go with that.
So let's say increase hydrophobicity. We don't know if alanine is nonpolar.
Mm-hmm. Yeah, and like valine,
It's
methionine,
also,
leucine,
yeah.
and isoleucine are also
Okay.
non-polar. So the only thing that's gonna really change is steric constraints, I think. Yeah,
Mm.
it's smaller in size. So it's also hydrophobic, but smaller in size.
I mean, because none of them are basic, we can
Correct.
just, okay.
Mm-hmm.
They're non-polar, so they can be hydrophobic. Sorry, increase hydrophilicity. Oh yeah, they're not hydrophilic. And
Mm-hmm.
then this is not a change because they're all hydrophobic. Okay.
Okay.
To
Go
the
to the second paragraph. So okay, BSA, right?
mm-hmm.
It says 50% of the mass of protein found in blood serum and mobilizes proteins and lipids, right?
BSA constitutes up to 50% of the mass of protein found in blood, serum, and molasses. Okay.
Um, okay, so what's the purpose of it? Let's see. So all right, they took the compound one, put it in saline, and put it in something with an enzyme catalyst. Okay. And then they added the protein. So okay. They added the protein solution with the bovine serum albumin, and it just mobilizes proteins and lipids. So it basically, let's see. Experiment was initiated by adding the protein. So, okay, first they added compound one, and then they added the enzyme catalyst. And then they added a protein with BSA.
Already included BSA.
So it's not, let's, can you see the top again? All right. Okay, so they were trying to look at the kinetics of esterases. All right. and they used compound 1 as a substrate. So esterase works to make compound 1 into like compound 2. So they added compound 1, and then they added the enzyme catalyst, and then protein solution. Damn. I don't know if it's going to be a co-catalyst or like I know albumin works to transport as a transport protein in like our blood, but I'm trying to see if the when they say addition of the enzyme catalyst, are they saying the enzyme itself is the catalyst or catalyst?
Yeah, it says so. It
Okay.
says compound 1 was dissolved in phosphate buffer saline so that its final concentration
Mhm.
in the first well was 10 micromolar. Yeah, so they added the enzyme catalyst and then they added the PBS so that the final concentration was 10 micromolar, I believe.
Mm-hmm.
So enzyme catalyst or compound 1 plus PBS equals 10 micromolar or equals a volume of or molarity of 10 micromolar, I guess.
Enzyme catalyst, is that the esterase
I think that was
or is that in the protein solution? All right, so it acts to mobilize proteins and lipids. So if that's what makes me think of B. If it means making it more mobile, unless it means that it was initiated by adding. I'm thinking of co-catalyst then. Co-catalyst. I
but
don't
why
think
would you
it'll
think it's
be
a co-catalyst?
just because it said it was initiated by it and it mobilizes it. So the esterase, let's say without it, won't work as quickly as if the albumin was there, which would mobilize the esterase. Now, mobilize could either mean make it in a form that is more mobile and therefore moves, which means it won't adhere to the walls of the vessel, which I don't know why it would do in the first place. Or by mobilization, they might mean it just gets it going, which would make me lean towards acts as a co-catalyst. Buffer the solution from changes in pH. That's kind of handled by the phosphate buffered saline part, so it shouldn't be C. Non-specific target for protease contaminants. I mean, if there are some proteases that have contaminated the sample, it would break down the esterase, which we don't want. So maybe if it acts, I don't think it would be this, but
Well, like a
protease.
distractor to
Yeah. So I'm between A and B here, but let's see. Initiated by adding this protein solution. So okay, all right. So the protein solution is added, and the BSA makes that protein solution like it helps you use the protein.
it. So it mobilizes a protein that needs to be used by the. Sorry,
Mm-hmm.
that is the substrate for the esterase.
Yeah. So co-catalyst or I'm gonna go with A.
Yeah, I mean, it's not like I understand what's going on, but I would go by A.
Damn it, B.
Let's see.
So it does mean mobile, like, because there's two ways of using the word mobilize, right? Like mobilize means to go into movement, and mobilize means, well, if you go into movement, it means that you're starting it, you're getting it going.
Right.
So, but it's more of the movement part. So the only reason I didn't go with B, because I was between A and B, was because I couldn't think of a reason why esterase would adhere to the walls of the vessel. But if it did adhere to the walls of the vessel, it would be stationary and not mobile, right?
Right.
So,
So basically, this
is-
BSA is indirectly mobilizing.
yeah, it's directly like mobilizing it. Like it was just like what to take from the word mobilize. Like it means to go mobile, which is to move, but it also means to start. So I just so like if it was A, it's the start part. If it was B, it's the move part. I just was like, why would it stick to the walls of the vessel? But it is the movement part. So it's B. Because if it adhered to the walls of the vessel, the esterase isn't moving, right?
Mm-hmm.
It'll just stick to it.
So, okay, so let's say that it will be A. If it was a co-catalyst, the reaction still wouldn't take place because it would start it, but it will bind to the walls of the vessel.
Yeah.
Is that correct
I think
or not?
it's like mobilize, like direct definition would lead to choice B. Indirect would lead to choice A. And I guess direct is always better because they're testing you based on knowing like the mechanisms, not like what ultimately happens. Because ultimately, it acts, it acts to start, the overall like reaction, right?
Mm-hmm.
But that's like an indirect thing that happens ultimately. But main takeaway, I suppose, is just the fact that BSA works to kind of get the protein to be in constant movement, and sticking to the wall or a surface or whatever means no movement.
Right.
So the direct definition of mobilize, which is movement, right,
Mm-hmm.
is the way to go there.
Okay.
Yeah, that's like how albumin, like our fats, like in our bloodstream, they are transported through our albumin
Mm-hmm.
because they're not fats, since our blood is mostly water, right? And fats are hydrophobic, they're not going to be like very mobile in our bloodstream. So
Right.
albumin, acts as a transporter.
Okay. But in this case, it's not because of that.
Oh no, it's like that. It's because of that also.
Okay.
Because it acts as a transporter in a bloodstream, transport movement, right?
Right, but then the reason why albumin binds to the fats is because they're hydrophobic. But then
Well,
esterase.
proteins don't have to be hydrophobic though. But albumin still helps them move along.
Okay.
So overall, think of just the albumin as something that just helps something move.
Okay.
And therefore,
Kind of
without it,
potentiate the movement or
yeah. And therefore, without it, there won't be movement. And no movement means getting stuck, right? You're stuck to something you can't move.
Mm-hmm.
Yeah.
Okay.
So yeah, the direct answer is always the right one. So should have went with B there, but yeah. Does that make sense?
Yeah.
Okay.
What the only question I had is why I mean co-catalyst.
It's just too vague and indirect. Like, let me put it this way. So like albumin helps transport lipids in our bloodstream, right? So I could say, what's the purpose of albumin, right? Is it to make to like increase fat metabolism? Because without like albumin helps the fat move,
Got
right?
it.
Which eventually means like once it reaches its destination, it'll get metabolized. But that's indirect. But directly, albumin works to get it to the destination where it gets metabolized.
Right.
So yeah, it's like like the direct, like mechanistic kind of answer
Got
is
it.
usually is the right one for the MCAT and most of these tests. Okay, so catalytic efficiency, we're going to look at, that table, on the bottom. And so, I don't necessarily remember the catalytic efficiency like formula. I think it really is like, I think KCAT is like the
Or it's
turnover
K-cat.
number.
Yeah.
So I guess that's just the number of molecules that get turned into the thing that they get turned into per, second or whatever. Because, the unit is nothing per second. So it's probably like, number of molecules that gets converted into whatever product per second, right?
Okay.
Now, efficiency is usually always unit, like without a unit. So it's probably going to mean like, um, hmm. Well, okay. So like it'll probably be something with a low like KCAT or something. So,
Because
oh, you know what? It's probably wait, something with K maybe catalytic efficiency. So it should be like how many molecules are turned into product per like overall amount of molecules. But anyway, let's see.
a lower K-cat. Lower K-cat.
So let's just look at the choices and look at what's different. So let's see. 2.8 E neg 3, 1.3 E neg 3, it goes down. Then it goes down even more. So it just keeps going down, right? So it's either going to be V86A or I276A. Because if they're saying lowest, we know that the extremes are the highest one is, the V86A, right? And then the lowest one is I276A. The ones in the middle aren't at extremes.
Yeah.
So those shouldn't be the answer, right?
Okay.
Unless KM has something to do with it, because that might affect things.
No, I don't think KM affects K-cat now that I remember, because K-cat is
Turnover number.
is
I'm just trying to
turnover.
see
So
if it
regardless,
affects efficiency, but who knows? But let's
you want
see.
me to
Well, we
well
don't
what
know because we have to try to answer it without knowing it, right?
right.
So like, but even if we look at KM, right? Wait. Well, KM, the lowest one is the 0.3. So that's kind of weird, but the 170 is the highest and it's the lowest for the other thing. So at least that part's consistent.
That makes sense, yeah.
So let's see. So, okay, now something with a low turnover number, which is a KCAT, and then a really high KM, which means that the substrate concentration needs to be that high
In order
for
for
it to
VMAT.
be like whatever, half of Vmax, right?
Mm-hmm.
So, that kind of rings true for,
For D, right?
yeah. I wonder if Km over K. Oh wait. Oh no, like if Km over K cat is the efficiency. But anyway,
Isn't kcal like an intrinsic quality of the enzyme?
yeah.
So
So like
Km can be changed whenever there's an inhibitor or
you know what?
whatever.
Km over K cat should be equivalent to like V because it's some like micromoles per second, right?
Oh, that's true.
Oh wait, no. Sorry, that's Km times K cat. So never mind.
Km
Anyway,
times kcal will be molar over second. Yeah.
anyway, yeah, I would lean on that on D. All
Yeah.
right. Okay, it's the K cat over Km.
If V is
Oh,
just the ratio.
yeah, that makes sense then. Because oh yeah, Km times K cat is equal to K cat over K. Wait, what am I talking about? Basically, like what I was saying before with hold on, never mind. K cat over Km, it seems to be what? No, damn it. No, I was right, I guess. No. K cat
Kcat to Km is a
is
measure of catalytic
catalytic
efficiency.
efficiency. Yeah. Okay. So I'm trying to see like that's weird.
I
Oh,
guess
okay. So that does all right. So that turns into I guess that would be number of molecules changed to product per micromolar second. Anyway, catalytic efficiency. Um, I guess like yeah, I guess you can add that to an Anki note that it's Kcat over Km. But you see how the reasoning we used was like, either going to be V86A or I276A.
right. But then I thought, I mean, we based it off Kcat being the highest,
The lowest, you mean?
the lowest, sorry. So, and
Mm-hmm.
then we kind of like reinforced that that was the right answer because
Mm-hmm.
the Km happened to be high. But
Mm-hmm.
if Km it's not high for that particular enzyme that has a lower K that has the lowest Kcat, then
Yeah, because like high Km actually means that it sucks. It's not good at its job of being an enzyme, right?
right.
Km is just the substrate concentration at which it's half of V max.
Mm-hmm.
So if Km is high, it means that you need more substrate. So it's not very good. The enzyme's not very good at doing it, its job. That's why when you have like whatever competitive inhibition, like, you know, anyway, K like low K cat means that the enzyme's not very good, and high Km also means it's not very good.
Right. But then the efficiency is measured by the ratio of both. Or
Yeah. Yeah. And since we weren't sure of that, all we can see is that I276A involves two things which indicate that it's bad at being an enzyme. Kcat is low and Km is high.
got it.
Yeah. Okay. So PBS, right? 0.1 millimolar, right? So right,
Milli 0.1 milligrams.
0.1 milli. So in the second sentence of the paragraph under
Okay.
reaction one, compound.
Okay.
See that compound one? It says PBS basically in parentheses.
Yeah. Oh, okay. Yeah. So it was dissolved in phosphate buffer saline, pH 7.4, 0.1 millimolar of NaCl.
Yeah. So we're going to take 0.1 E neg 3 moles per liter, right?
Mm-hmm.
And we're going to multiply it by 100 E neg 6 liters, right? To get the moles. And then we can just multiply it by 58.5 grams per mole for the moles to cancel to get mass.
Right. So that would be, I'm sorry, this is where I get confused. I know it sounds stupid, but I see the 0.1 times 100 and I'm like, I don't know what to do.
Here, let me see. So so 0.1 E neg 3 times 100 E neg 6 times 55. Oh no, 58.5.
Right. So how would you do like in an easier way that 0.1 times 100?
First I'll just do, well, the 0.1 you can make 1/10, and then the 10 cancels out with the 100 to make the 100 just 10 E neg 6.
And that would be equal to 10.
So now I
E neg-
have 585 E neg 9. So it should be A.
Yeah.
So yeah, so you asked how to do the 0.1 times 100.
585. Hold on. I get, okay, so you say it's A, which is nanograms.
Yeah. So
But when you multiply 10 E negative 9 times 58.5, it's, I get 585 E neg 9.
Yep.
Sorry, E neg 8, because that 58.5, it's,
So okay. That first thing you asked, 0.1, right?
oh yeah, I did that one. Yeah, you said to just switch it to 1/10, and then if you multiply it by 100, then it cancels out the 10 because you divide 100 by 10. So basically,
Yeah.
it's just 1 times 10 equals 10 E neg 9.
So like the 1/10 E neg 3 turns into 1 E neg 3. The
Mm-hmm.
100 E neg 6 turns into 10 E neg 6.
Mm-hmm.
And then you multiply by 58.5. So then I just did 58.5 times 10 is 585.
Mm-hmm.
And then it'll just be 585. And then I deal with the exponents. So the neg 3 and the neg 6 turn into negative 9. So
Mm-hmm.
585 E neg 9.
But the 58.5 doesn't have an exponent of 1.
No, it has an exponent of 0.
That's why I thought it was -8. Why does it have an exponent of 0?
Because E is times 10 to the power of the thing after the E.
Right. Oh,
So if it's to the 1 power, it's times 10.
yeah.
And if it's times 10 to the 0 power, anything to the 0 power is 1.
Mm-hmm.
So yeah, the 55.
Where is it to the 0 power?
What's up?
Can we say it's to the 0 power?
Mhm.
Okay.
Yeah. So you could write 58.5 E0.
Mm-hmm. And then it will give you 585 E to the -9.
Mm-hmm.
Let me check this out.
But yeah, it doesn't help like when you ask how to do the 0.1 times 100, make it into 1/10.
Right. Yeah, no, it does, because I have a problem with decimals and I
Yeah,
just
yeah.
see them and I'm like, I know how to do this, but I just, so yeah,
Yeah.
of course, 1/10, and then you just simplify with the other number or
Yeah.
kind of divide.
So that's why, I always like fractions, right?
Mm-hmm.
Because I see, it's like that for everyone, like 0.1, and then it's like times 100, move the decimal point over, blah, blah, blah.
Yeah.
I just turned it into 1/10. It's
Okay.
just easier. Okay. That one made sense.
Yeah, I did.
Okay. So let's see. Why does the proposed mechanism involve deprotonation? Oh, this is a different one. Deprotonation prior to reaction. Deprotonation is described in the passage, causes the reacting. So, okay, this thing catalyzes the hydrolysis of a terminal peptide bond in a protein. Okay. All right. Something with glycine. All right. Active site has two pentacoordinate zinc ions. Okay. A and B. All right. Resting state of the enzyme has a bound water instead of a glycine. Okay. And then the mechanism of action, let's see. Scroll a little. Involves binding of the substrate, deprotonation of the bound water by glutamate at position 147, not shown, and then subsequent reaction with the substrate. The addition of water allows release of the substrate and a return to the resting state. Okay, so let's see. So the H seal thing, first it binds the substrate, and then some glutamate causes the bound water to be deprotonated. So okay. So if it's deprotonated, it's going to be, let's see, causes the reacting a subsequent reaction of the substrate. Um okay. Amine group to be more nucleophilic, carbonyl to be more okay. Can you go up to the top again? Okay, so the enzyme works to catalyze hydrolysis. All right, and then bound water instead of a glycine. Okay, so at that bottom there should be a water instead of a glycine. Okay, now
I'm gonna use the restroom really quick,
sure.
but I'll be back.
Okay. Okay. So okay, this is an enzyme that breaks a peptide bond. So through hydrolysis. So, and they're asking about causes the reacting something to happen, right? So the reacting something is either going to be um like a peptide or water. Um and can you scroll down a little bit?
Yeah.
Okay. Binding of the substrate, deprotonation of bound water, and subsequent reaction with the substrate. So if the water is deprotonated, it'd be negative OH. And then that should attack. I think it'll be maybe C.
The water molecule to be more nucleophilic.
Because you're gonna need the water to assist in hydrolysis of the peptide bond. It could be any of these, but I'm gonna think maybe C. Okay, so deprotonation of the reacting water will make it more nucleophilic and reactive towards the electrophilic carbonyl atom of the amide functional group. Yeah, so like we know that an amine group is going to be nucleophilic. We know that the carbonyl group will be electrophilic. But they're asking specifically about deprotonation of the water. And that is affecting the water. Because like the substrate is going to be, let's say, a peptide, right?
Mm-hmm.
And the enzyme is going to cause that peptide bond to break. So, right?
Right.
So through the addition of water.
To the addition of water to the bond or to the enzyme?
To the enzyme is going to bring together
The
that
water.
and the water, and it's going to cause hydrolysis, right? Opposite of dehydration synthesis,
Mm-hmm.
to break that peptide bond.
Mm-hmm.
So A and B both are saying things that are true about a peptide bond, but they're asking, what does deprotonation cause? And
You said A and B are causing.
A and B are true statements,
Okay.
but well, everything here is a true statement, but zinc is out because they're asking about the reacting something. So they're asking about a reactant. And zinc is just part of the enzyme. So zinc, the choice D is out.
Mm-hmm.
And A and B are talking about the reactant peptide. And C is talking about the reactant water.
Molecule. Right.
Mhm.
So deprotonating water cannot really make the
Won't
amine
really,
group more nucleophilic. What I mean,
yeah,
not really. Yeah.
you won't really change the peptide, which has a nucleophilic amine group and a electrophilic carbonyl group. Like
Right.
it's true that the peptide has that, but they're saying, what does deprotonation of water cause? And the
Mm-hmm.
only thing that it can cause is, something to happen to the water itself. So the water becomes nucleophilic, and that's that's what happens.
Okay.
So like, see how they're all true statements,
Yep.
but
Well, these Yeah, the first
The
three.
first thing I looked at is the word reacting in the question. Like causes the
The
reacting.
reacting what? Yeah.
So if something reacts, right? Like it's a reactant.
Right.
It can't be the enzyme. The enzyme doesn't change.
Mm-hmm.
So and zinc is a part of the enzyme. So that's out. Can't be the answer.
Right. Okay, but then the peptide bond is also a reactant though.
Yeah.
But
So
the protonation is not being done to the peptide bond. It's being
yeah,
done to water.
correct.
Okay.
So that's how I narrowed it down. So first thing I looked at reacting, which means D is out. Then I looked at deprotonation, which is specifically only changing water. So
Mhm.
yeah, it would be C.
Got it.
Okay. Why do the researchers choose A as a replacement residue for each of the single site variants used in the study? Use of A. Okay, so let's see. So A, they're talking about that zinc on the left, I think. So like, all right, and then scroll down, they probably talked about that. Okay, so no, never mind. They're talking about making it alanine again.
Choose A as the replacement residue for each of the single site variants used in the study. Oh, choose. Oh, like, are they talking about the amino acid?
Mm-hmm.
Why do they have to say A instead of like alanine? I thought it was A was a compound or like some sort of like molecule named compound A.
Yeah, initially I thought they meant zinc A, but they said residue, right? And
Yeah,
residue is an amino acid residue. And then they said single site variants, and table 1 gives you those variants, like
right.
yggdrasil variant.
Mm-hmm.
So yeah,
Okay, so this is similar to the other question of
correct.
reducing steric hindrance or yeah, whatever it was.
Mm-hmm.
So let's see. Histidine for alanine. These are all charged. So reduces the net charge on the bimetallic center. Reduces the interaction with the side chain with other active site. Increase the carbon. Okay, so all I know is that something that is histidine is positively charged. So either something basic or acidic, which is charged, is gonna be changed for something that is hydrophobic, which is alanine, right?
Mm-hmm. And also Km is higher for all of these variants, which means that its binding affinity is lower
How do you know that the Km is higher?
because the wild type is 0.43
Oh,
and
hold on,
everything.
give me 1 second.
Yep.
I'm sorry.
Mm-hmm.
Okay, so the Km is higher for every of the variants compared to the wild type. Okay, so it's decreasing the affinity.
Yeah, so it won't be B. And I mean, it's going to be the same thing as the other one, which is basically reduces interaction of the side chain with other active site components. Because it's turning it into like a neutral molecule, right? Because if it's charged, it can interact with other things because it's, charged, right?
Mm-hmm. What about reduces the net? I really thought, or at least I thought, oh, it reduces the net charge because it's turning from a charged variant to a uncharged variant.
Yeah, but it says on the bimetallic center, right?
I don't even know what that means.
That's that center between the two metals, zinc ions. Like
Okay,
up, if you look at the thing, the diagram, I mean the picture of the yeah,
oh,
that
okay.
center, that's like where the thing binds, and
Mm-hmm.
it's between the zinc on the left and the zinc on the right.
So it's
So
not really affecting that.
correct.
Okay. And then increases the conformational rigidity. Can we assume that that increase in conformational rigidity will be an increase in the affinity?
So you can see that based on, go back to that table, the Tm, that's the temperature at which it starts to denature, right?
Mm-hmm.
And it's 64 normally, all the variants, it's lower. So it starts to denature at a lower temperature. So it's less stable, less, rigid.
Is that what it means though? Is
Mm-hmm.
conformational rigidity the same thing as stable?
Mm-hmm.
Okay.
Because think about it, with if you increase the temperature, right, it stops being rigid, it starts moving around, and it starts to become less stable and starts to break down.
Mm-hmm.
So yeah, so Tm shows that it's getting less conformationally rigid.
Um, did
Mhm.
you know what TM meant? Or did they say here what TM was?
It does also melting temperature,
Melting temperature. Okay, got it.
but I see questions like that a lot with um, DNA that has GC, like a bond between G and C. It's three
Mm-hmm. Three
hydrogen
hydrogen
bonds.
bonds instead
So
of
the
eight.
TM for part of a DNA that has more GC content is
It's
higher.
higher. Okay.
Correct. So, so yeah, it reduces interaction of the side chain with other active site components.
Oh, sorry. I didn't pick the.
Yeah, because it's small and it's not, and it's neutral, so it just minds its own business.
Mm-hmm.
So that's gonna be it.
Okay.
I hope. Yeah,
Uh, yeah, we already worked through that answer choice. We didn't want it to be wrong.
of course.
All right. I guess we can do one more.
Okay. Um. Okay. So the observed TM.
What is
Um.
the best conclusion regarding the role of the metal centers?
Yeah. So all those variants.
I
I
don't think it's
mean,
this one.
I think it is that one.
How would they provide conformational stability if uh I mean they all of these variants they still have the bimetallic center, no?
Yeah.
So if their conformational stability is changing by changing the amino acids, but they still have the common denominator of having the same metallic center, then it shouldn't be playing any role in conformational stability.
Um. Let's see. So let me see that picture. Okay, so the zinc stuff is near, let's see, 148, 175 and stuff. Okay, let's see the bottom again. Okay, so all right, so they're changing all of the things that are related to the zinc thing, right? Like 113, 147, 148, 175, 373. They're all like
Oh, okay.
373, 175, 148, right? So
Mm-hmm.
they're changing them, right? So that's going to basically make them not connected to the zinc things.
Right,
And TM goes down.
right.
So that means the zinc things should work to provide conformational stability. And since KCAT is also going down, they should work on catalysis as well. And it's going to be both, since it's for all of them, right? If it was just for like whichever, like 80 and 148, that would be zinc A. But it's for the things that are for zinc B also.
But wait, so when they're talking about the role of the metal centers, you told me that okay, so this whole thing is a metal center?
No, just like the middle part.
Right. So
Mm-hmm.
that's what I got confused. And I was like, if what they're changing on the variants are this like
Mm-hmm.
these parts, right?
Mm-hmm.
Which are not part of the metal center though.
Mm-hmm.
And then when they change them, like they did here,
Yeah.
the KM goes down. Sorry, the KM goes up and the TM goes down.
Yeah, and the KCAT goes down.
Exactly. But they all share the same metal center. Like the metal center is not being affected in any of these changes.
So
Then why would it be
uh-huh.
playing a role in conformational stability if it's
Uh
going down?
so okay, let's take H80A, right?
Yeah.
All right, now go up to the top. See that H80?
Mm-hmm.
So that's like the histidine. You see that, like, whatever group.
Right.
So let's say it's no longer histidine. So that group's not there, right?
Okay.
So that connection with the zinc A is severed
Right.
when you turn it into alanine. Now, let's say we did that with E148, right?
Mm-hmm.
Made it alanine. That connection's severed
But how do you know the connection is being severed?
because it needs to be, E148, needs to be H80, right?
Okay.
And see the H373
Mm-hmm.
and the E175.
Yeah. Wait,
Like
but this is not part of the amino acid.
it is actually.
This double,
Mm-hmm.
what? Did I forget the structure of it?
Uh, it's okay because I don't remember it either, but we know that histidine has that ring, right?
Right. Yeah.
So it must mean that whatever glutamic acid, right,
Mm-hmm.
would be those two O's.
Okay. So then once you replace that amino acid, it severs the connection with either
Mm-hmm.
sync A or sync B,
Yep. Yeah.
which decreases the stability and also decreases the Km,
Well,
increases the Km.
yeah, but we're really just looking at stability we look at with TM and catalysis through KCAT. So if we just saw, the decrease in KCAT and TM for the change in H80 and E 148, I think it was, then it would
Mm-hmm.
just be zinc A, right?
Mm-hmm.
Um,
Oh, okay. So only a decrease here on this side.
Yeah. So like for instance, choice A, right? If
Mhm.
we saw,
Oh, got it.
so that means that if we saw like, when zinc A was severed, the K-cat would decrease, but when the things for zinc B are severed, so when zinc A is severed, K-cat would go down, but TM would stay the same.
Mhm.
And when the amino acids attached to the ZNB, when that is severed and we see K-cat is the same, but TM decrease, then that would mean that choice A is the right answer, because that's saying that zinc A is the part that's responsible for the catalysis, and zinc B is the part that's responsible for stability. Stability
Yeah,
is
you
the
know what?
TM.
I
Hmm?
hadn't looked at the other answer choices, and
Mhm.
I didn't know that there was an option saying that sync A would do this and sync B would do this.
Yeah. So I would look at the question like this. So like always look at the answer choices, because you know, just
They will hint you as to what is it that they're trying to.
yeah. So like I see that, choice A and choice B separates catalysis from conformational stability, right?
Mm-hmm.
And so I would look at the table and see that to measure catalysis, I would look at K-cat, and to
Mm-hmm.
measure conformational stability, I would look at TM.
Right.
And and then I find that the ones that are related to or connected to zinc A, like
Mm-hmm.
if that, what changed with that, and it seems like the K-cat went down
Mm-hmm.
and the conformational stability went down, the TM went down.
Right.
And then for zinc B, the things attached to that, same thing. The K-cat went down and the TM went down.
Right.
So both of them, when when both are severed, right,
That's true.
everything goes down. So that means that both of them, when they're there and not severed, K-cat goes up, which it does in the wild type, and TM goes up, which it does in the wild type. So both of them are involved in catalysis and both provide conformational stability. Make sense?
Makes 100% sense.
Okay.
Yeah.
Yep.
Cool.
See how they talk about K-cat and then TM and stuff?
Lower TM as well as the catalytic rate as evidenced by lower values for K-cat. Yep. Yeah, I should have looked at the answer choices.
Yeah, always look at the choices, because a lot of times, it just helps you like kind of sort through the information like better and faster.
Mm-hmm.
And also like, you can kind of figure things out based on like whatever the answer choices, because they, you know, they I don't know, they're just like, yeah, they're good clues.
Right, they're clues to us what you have to look at in passage. Okay,
Mhm.
cool. All right.
Is there like how many more are there for this passage? I think we can.
Let's see. 1, 2. How many? Oh my gosh, how many questions? 3? How many questions were there? Were 5? I thought we have done more.
Yeah, that's crazy.
Yeah.
We
There's
could do
3 more.
the others if you want.
Okay.
All right, let's do it. So, what's the best explanation for the observed behavior of the E147D variant? So they talk about it in the whatever passage. I
Mm-hmm.
think where the temperature goes down. Yeah, the E147D variant exhibited a TM of less than 37 degrees and did not exhibit amino cyclase activity. Right. So basically, its stability went to crap, and its catalytic whatever
Went down.
catalytic catalysis whatever went down as well, right? All right,
Mm-hmm.
now what does the substitution result in? So I mean, glutamate is turned into aspartic acid, right?
Mm-hmm.
So okay, so then what does that? Okay, so it shouldn't change the reactivity of the zinc. I forgot which one's bigger, so I don't know about the steric hindrance part. Um, increase the site to act as a general base. I'm not sure about that. A repulsive interaction that reduces conformational stability. That's the only one that says reduces
Both,
conformational stability.
yeah.
So I'm gonna go with that. Yeah. So see how like looking at the choices, at first it's like, all right, this means I'm gonna look at this, I'm gonna look at this, but only one of them talked about the things we were looking for, catalysis and catalytic stability or conformational stability. So it must be that one. That's the only choice. Like it could be due to any other reason. Like if it said increased steric hindrance at the active site and caused reduced conformational stability and thus enzymatic activity, then we would have to look into that
Into
further.
that one. Yeah.
But since that's the only choice that has that answer, it must be true.
Well, so steric hindrance of the and reduces access by the substrate. So I would think that indirectly by reducing access to the substrate, they're reducing the catalytic. Well, no, not really. I'm just trying to make up something.
No, that it would reduce the catalytic
But
efficiency.
not in reality. I mean, indirectly, but
No, it would. It would
it
just
would.
it would, but it wouldn't affect the conformational stability, right?
And
The
you need both.
TM. Like it's steric hindrance, which means that the active site has too much stuff blocking it, so the substrate can't bind to it as strongly. So it causes the KCAT to go down, but it doesn't say anything about conformational stability. It doesn't say anything about the TM.
Okay.
So yeah. This one, assuming binding is fast relative to subsequent catalytic steps, what relative effect does substituting the various active site residues have on catalytic versus, on catalysis versus substrate binding? Okay.
Oh, so it's really just, can we compare KM to KCAT?
Yeah. Well, okay. KM just seems to quadruple at first, and then it goes to like 0.57, which is pretty similar to wild type. So I don't see much of a difference in KM. However, all the KCATs are like to the, -3 power. So they're like basically like you go from 39 to like 0.016, right? To like really, really tiny numbers.
Oh, yeah, of course.
So it's going to be, and KM is related to substrate binding. KCAT is related to catalytic turnover.
Over.
So that more so, yeah, should be that one.
Oh my God. That is awesome.
Yep. And I think there's one more. All right. So, okay. Peptide bond, right, has double bond like characteristics. So it starts at sp2.
Then, so the reacting substrate carbon and the mechanism described by Sandra goes, which of the following hybridization state changes during the reaction? I don't even know what carbon they're talking about.
Like they're talking about the peptide bond.
Oh.
Mm-hmm.
How do you know that?
Because they're saying the reacting substrate carbon, right? And remember the reactants are just the peptide and the water. Yeah.
In the mechanism described in the passage. Okay, it can be the reacting substrate carbon from the peptide bond, or it can be the reacting substrate. Never mind, water doesn't have carbon. That was a really stupid comment. Sorry.
What? No,
I was like, what? Why it can't be from water though? But yeah, okay. So it will be the carbonyl, the carbonyl. So what happens there is that water reacts.
So like, all right, so any like peptide bond, it turns into like something that has like whatever this type of like resonance to it, which makes it like planar. and that's sp2, and the only thing that starts out with sp2 is A. So it'll be that.
Is it because,
Yeah. See if you can
repeat what you said
Google
again? So
Google
the
image search.
intermediate will be that alcohol attacking that carbon on the carbonyl, right? That's the intermediate.
Yeah, do a Google image search for peptide bond. All right, now let's see. Scroll down. Keep going.
Right. Okay.
Oh wait, yeah, right there. Yeah. There's double bond character in a peptide bond. Because see, so like the thing on the left, that's like the peptide bond, but it has resonance with the thing on the right. So therefore, you know, it's planar, right? Like 120 degrees. Like
Right.
you know, like what's meant by like sp2, sp3, sp.
Yeah. The hybridization
Yeah.
state or the figure, yeah.
Yes, like sp3 is like a single bond, like free
Right.
rotation. Sp2 is like, you know, with double bond, so like 120 degrees, right? Like trigonal planar. And sp3, sp just regular is like a triple bond or like linear. Yeah. So you know, remember that. Maybe make like an Anki card about it. But peptide bonds always have this type of like double bond character.
Right. But so my question was like here where it says the middle hybridization state refers to an intermediate. Is it sp3 just because it would be that carbonyl, that carbon of the carbonyl binding temporarily to the OH from the water?
Yeah, it'll be that whatever tetrahedral intermediate or something.
Right.
But it was the only one that started with an sp2.
And I don't even need to go into, I don't even need to go into the other step. Just know that it has to be one that starts with sp2.
Yeah, but let's say you had another one with sp2, right?
Right.
Then so okay, we're breaking a peptide bond, and let me see that question again. So all right, which of the following? Okay, so and then let's go to the top of the passage. So we know that it catalyzes, so it breaks a peptide bond, or the hydrolysis of N-acyl amino acids. I mean, yeah, I mean, yeah. I don't know. Like, yeah.
Thank God there was not another answer choice with sp2.
Yeah.
That's all we have to say.
Like, yeah. Well, let's say there was another one that had sp2. You know, like in the middle, it would have to be sp3 again. Because of
And
that.
then back to the original.
Yeah, because then that OH part leaves. So, yeah.
Got it.
All right. Makes sense?
That's it. Yeah.
Right. Okay. Anything else for now?
No, I mean, you can't really do any like hours in the morning, right?
Depends on how early.
So I work at 11 and I work like 5 minutes away from my apartment. So
Yeah.
I can do like, I mean, I can do even an hour. I don't care at this point as long as I can do some questions. So I go like we can do 9:30 to 10:30.
Do you have like what's your availability like for like not the mornings?
Then after that I get out of work at 11 p.m. So yeah, it's pretty late.
But like the days that you have.
Oh, nothing. I'm gonna be studying the rest of the day. So yeah. The next day that I have off is on Monday though.
Monday, and then like what about like that week?
Then I work Tuesday and that's it. I'm off until the 4th of May.
Okay.
Much.
All right. So we could do like a lot like those days during like
right.
Like
okay.
not morning, right?
You're not a morning person. I get it.
No.
Not at all.
Yeah.
Okay. All right, let's do
Does
that.
that
So
work?
I'll text you on Monday so we can
Okay.
do some on Monday.
Awesome.
Don't forget to request me the money because
Oh, yeah.
like, yeah, that's it. Okay,
Okay.
thank you so much.
All right.
Bye.
No problem. All right. Take care. Bye.